Near the end of the second video, they start talking about little decay equations. So we want to look at this. We're going to be talking about alpha decay, in which an alpha particle is given off, and that's what's happening here on our title screen. A beta particle, where a beta is shot out of the nucleus, and in combination of those, sometimes we get gamma emission. And we know gamma is a form of light, so that just reduces the energy of the nucleus. Now, any time that we end up with a different element than we started with, then officially that's transmutation. We should recognize that. And some of the times we want to find out, well, what is actually changing? You know, is it just particles going off, or is something else more interesting going on? The first example they showed us here was radon 212. Now, in radon 212, a lot of times we write the symbol like this, the isotopic symbol, but we know that radon, okay, way down here in our periodic table, you know, is number 86. So on our symbol, we're going to put 86. But I want you to notice also that this one says 222, and our radon up here is only 212. And that's important, that this top number, the mass number, does not really have to match our periodic table. Now this part does have to match this. You know, this is 86. Any radon has 86 protons. 86 protons is going to be radon always. Now this, when we say this is alpha decay, that means it's going to shoot off an alpha particle, and it means the alpha particle is going to show up on the right side of the equation. Now an alpha particle is 2 protons and 2 neutrons, so anything with 2 protons is going to be helium, we can see on our periodic table, and if it has 2 protons and 2 neutrons, we can see that the mass is going to be 4. So this little symbol here, that's the alpha particle, and we should memorize that because we're going to need it. So if it says alpha decay, all we have to do is put in this particle, helium 4 over 2. And then this part is very simple, just the numbers have to match up. The top numbers on the right side of the arrow equal the top numbers on the left side, and same thing with the bottom numbers. So 212 must be 4 plus 208, and 86 must be 2 plus 84. So we go back and look at our periodic table and say, who's number 84? 84 is down here, polonium. So we put in our symbol then here, polonium. And that's our decay equation, our nuclear equation. And this whole thing, since it gives off an alpha particle, then this is called alpha decay. Now once in a while we're going to see particles on the left side of the arrow as well. Okay, but if you see decay, then that pretty much means that particle shows up on the right side of the arrow, one of the products. Now the second one they showed in the movie there is one called beta decay. So here's our carbon, and we can see by our carbon here that carbon has 6 protons. 6 protons. So we want to go back and fix our symbol here. Put the 6 down here at the bottom. That's important. Now beta particle, notice, is a high-speed electron. So this is going to be called beta decay. Now when we're doing these symbols, a lot of times we said, well, the upper number, that is the mass number, the bottom number is the atomic number. The top number is the number of protons and neutrons, and this bottom number here, that's the number of protons. But another way to look at that is to say that the top number is the charge, the top number is the mass, and the bottom number is the charge. And that's a useful way to think about when we're thinking about an electron. So what's the charge on an electron? You know, it's a -1, because it wouldn't make any sense to say, well, how many protons in an electron? And the top is the mass. The mass is essentially 0 compared to protons and neutrons. So when we have beta decay, then we write a beta particle, E0 -1, and then we do the rest of the numbers. So the top number there must be 14, and the bottom here must be, okay, this we have to be careful. So a lot of times if you're in a hurry, you look at the problem, you say 6 minus 1 is 5, and that's incorrect, okay, because the numbers on the side, this must be 7. 7 minus 1 is equal to 6. So maybe working from right to left might be a better way to do this. So we have to go back and say, well, who is element 7? We can see element 7 here, that's nitrogen. So let's write that in. Now we do want to look at this just for a moment. I'm going to clean up my moment here. I've rewritten my equation to give myself a little bit of room because we want to go back and see, well, what's happening here? On the carbon, since it's number 6, we know that it has 6 protons. And when we're done, our nitrogen, since it's atomic number 7, we have 7 protons. And I made a little mistake here. Let me fix this. Okay, this up top should be 14, not 7. Okay, now, because the carbon weighs 14 and it has 6 protons, it must have 8 neutrons. And the same thing with our nitrogen, because it has a mass of 14, it must have 7 neutrons, because 7 and 7 is 14. So what has happened in this equation is we have 8 neutrons turning into 7 neutrons. We lost a neutron, but we have 6 protons turning into 7 protons, so we gained a proton. So in this process, a neutron has changed into a proton. A neutron is changed into a proton. That's not something we would normally think is going to happen, but it just did. And so if we have something neutral turned into something positive, then it's not surprising we also get something negative, and that negative thing is our beta particle. So during beta decay, a neutron changes into a proton and an electron. Now, here we have the third example, and that was gamma emission. Now, gamma can happen when other reactions also happen. So let's go back here for our phosphorus. Okay, phosphorus is number 15. So we'll write a 15 down here. Now, this equation, they're saying, well, let's go ahead and say this is going to be beta decay. So we put in a beta particle, and it gives off a gamma. Now, gamma is our gamma symbol. It's actually light, so it has no mass, and it has no charge. So you can see it doesn't really change any of our numbers, and that's okay. But sometimes the nucleus is excited, and when it relaxes back to a normal state, it's kind of like a excited state atom going to the ground state atom. It has to give off some energy, and that energy comes off in the form of light. So we'll do our numbers. Top 31 equals 31, plus 0, plus 0. 15, again, minus 1. So what minus 1 gives us 15? That would be 16, and that would be sulfur. So in this case, we would call this reaction beta decay. With gamma emission. So, two things here. If we see the word emission or we see the word decay, then that pretty much means that the particles are going to be on the right side of the arrow. Now, there will be another situation where if we say neutron bombardment, that would be on the left side. Electron capture, that would be on the left side. Now, we were looking at this. We've seen alpha decay, we've seen beta decay, we've seen gamma emission. Okay, we talked about what changes, but did we have transmutation? Here we started with phosphorus, we ended with sulfur, so this beta decay would be transmutation. Same thing here, we started with carbon, we ended up with nitrogen, so that was a transmutation. Radon going to polonium, also a transmutation. So each of those would have been a transmutation. That's it.